Welcome to this first module of the Fundamentals of Machine Learning program at Aon Intelligence. My name is Marcel de Sutter, and today I'll be giving you an introduction to regression and kernel methods. So this is my plan for today. I'll start with some prerequisites that I expected to know in order to be able to follow the material of this module, but the entire Fundamentals of Machine Learning program as a whole, before we'll start with actual content. So we'll dive into what I call the basics of machine learning, and this includes a mathematical description of what we're doing, a formal setup, before we then turn our attention to the linear regression algorithm, which will serve as a prime example of a machine learning algorithm with which we can already see a lot of concepts that will reoccur time and time again when we deal with some more advanced concepts. Then I want to spend some time talking about the kernel trick. And this is something that I think is poorly understood by many data scientists and machine learning engineers. So I'll definitely spend some time explaining the kernel trick so that once you're done with this module, you definitely have a solid understanding of what it is. Then we'll study some more advanced concepts like the reproducing kernel Hilbert spaces. And these are the spaces of functions that we implicitly define by using a kernel. And the functions in such function spaces exhibit really nice properties. So we're going to investigate those. And then we'll study what's called the Gaussian processes. And this is a natural extension to the linear regression algorithm. So linear regression, we produce a point estimate. You give me an input and I will produce a real number for you. And there's no confidence measure associated with this estimation. And with Gaussian processes, we get a density around our estimation for free, basically. So essentially, the Gaussian processes are a straight upgrade to the linear regression estimation. And also, it's highly practical because when you're tasked with producing an estimation, then usually what people would like to see is a confidence bound around your estimation, a range of values that you assign some confidence to. And finally, we'll spend some time investigating the relationship between kernels and Gaussian processes, because these two concepts might seem distinct, but there are some really deep connections that I will illuminate for you. And at the end, there will be some slides that will indicate what awaits you in the next module. So let's get started with the prerequisites. So with regards to linear algebra, I expected to know the fundamental objects that we're going to manipulate all the time, which are scalars, vectors, and matrices, and you should be able to do basic operations on them, as well as know what vector norms are. But let's go through it one by one. So a scalar is technically an element of a field over which you define a vector space. But let's not be too formal about that. For our purposes, usually scalars are either real numbers or sometimes complex ones. So vectors technically are elements of the vector space that we define, but for our purposes, usually these will just be real valued vectors with the dimensionality d. And then there are matrices, and these are technically linear mappings between vector spaces, but for our purposes, again, these are just like tables containing numbers, and they have n rows and d columns, and thus have the dimension n times d. And then we have basic operations on those objects. So you should be able to add and subtract vectors. You should be able to calculate the inner product of two vectors, or the scalar product, it's also sometimes called. You should be able to do matrix vector multiplication, as well as adding and subtracting matrices from other matrices. You should also be able to first find the transpose of a matrix before multiplying that matrix with another matrix. For square matrices, you should be able to find the trace, so the sum of the diagonal entries, and the determinant. Well, technically, you don't have to be able to find the determinant for matrices that are larger than, say, 3 by 3, because I don't know how to do that myself. But you should have some intuition of what the determinant represents. And then the inverses of matrices shouldn't be a mystery to you either. And with regards to vector norms, if you know about the L1 and the L2 norm of a vector already, then that's great. But you don't have to, because we'll be introducing vector norms formally in this course or in this module. So let's see if you can do these basic manipulations. So these exercises are not designed to be hard. It's just for you to check your knowledge. I guess I'll take a minute to fill this out myself, and then we compare results. So see you in a bit. So I hope this wasn't too difficult for you. So let's start with this one. We have alpha times x, and we just insert the values as defined above. And we see that alpha is a scalar, x is a vector, and what we do in such cases is that we multiply the scalar with each element, each component of x. And this is the meaning of a scalar, actually, that you scale the vector by the magnitude that is defined by that scalar. And yeah, we end up with the vector 3, 6, 9. And then the inner product of the vectors x and y is defined as the sum of the element-wise products. Okay, so we take the 1 multiplied with the 6, we take the 2 multiplied with the 5, the 3 with the 4, and then we add up all these products. And if we do this, we arrive at 28. Note that the inner product is also called the scalar product, because by doing this operation, you produce a scalar again. Right? You reduce two vectors and produce a scalar. Then we have the matrix vector multiplication AX, and we just write down the definition of A as well as the definition of X. So there are different ways to visualize this matrix vector multiplication, but what I like to do is that I take this column vector and mentally transpose it into a row vector, so that I can now calculate the inner product between these values and the first row of the matrix A. And if we do this, so it's similar to what we have here, we arrive at 1 times 1 plus 3 times 3. And if we do the same procedure for the second row, so calculate the inner product between these values and these, then we end up with the 3 times 2. If we then evaluate these quantities, we are left with the vector 10, 6. Now for this matrix multiplication, we first have to transpose A. And when transposing, we turn rows into columns and columns into rows. So we are left with this object as A transposed. And from the right, we multiply the matrix B as defined above. And we basically do the same as in the previous problem. We take these entries, turn them into a row vector, essentially, and calculate the inner product between these values and these. And that's our first entry. We do this again with these entries and the second row of A transpose. And then finally with these entries and the third row of A transpose. And we are left with this column of our output matrix. And finally, we repeat this entire procedure, this time with these two values. And this will then be our resulting matrix. And then for the trace of B, this is actually quite simple. We just take the sum of the diagonal entries of B, so 6 plus 3, and this is equal to 9. So for calculating the determinant, there are some formulas that you could employ. For this particular case of a matrix being dimensionality 2 by 2, there's this formula that states the determinant is equal to these diagonal entries. You multiply them, and then you subtract the product of the off diagonals. And in that case, it would be 6 times 3 minus 5 times 4. Then we have 18 minus 20, which is equal to minus 2. So the determinant of B is minus 2. Now the L1 norm, as we will see later in this module, is defined as the sum of the absolute values of the entries of X. So in this case, it's the absolute value of 1, the absolute value of 2, the absolute value of 3. You calculate the sum of those, and since they're all positive anyway, it's just an ordinary sum, and you arrive at the conclusion that the L1 norm of X is equal to 6. Now the L2 norm is defined slightly differently. So you want to end up with positive values as well. So what you do is that you square the entries of x, which makes them positive. You add up all of them, and then to undo your squaring, you take the square root of that entire sum. And applying this to x means that we have 1 to the power of 2 plus 2 to the power of 2 plus 3 to the power of 2, and then we take the square root of that, and this is equal to the square root of 14. So I hope you got all of this right. Let's see what else we have in store. There's also a little bit of multivariable calculus that I expected to know. Namely, the notion of a function should be really clear to you. So in this case, this function f is a univariate function. Also, the output is univariate. We might have functions, let's denote them by psi, that have a d-dimensional input. We call these functions multivariate. So they take as input a vector of dimensionality d, and this particular function produces a scalar as output. But we could also have functions phi that have a multivariate input of dimension d, and they could also produce a vector as output, not necessarily of the same dimension. So let's denote it with n. And then there might be functions that have matrix valued input, and they produce matrices as output. Now, based on these different kinds of functions, which differ in the input and output dimensionality, you can find different kinds of derivatives. So in the univariate case, where f just takes one variable as input, you can find the derivative with respect to that particular input. And if f is at least k times differentiable, you can find the kth derivative with respect to that input variable. If you have a multivariate function that has a vector valued input, then you can find the what's called partial derivative of psi with respect to any of the entries of the input vector. You can also find higher order partial derivatives of this function psi. In this case, it's the second order partial derivative. First with respect to xy, and then with respect to xj. If you have a function phi that has n-dimensional output, you can find the partial derivative of the nth entry of the output vector with respect to any of the entries of the input vector. And this is what I mean with this notation. Now, the good thing is that there's not much more that I expected to know about multivariable calculus. We'll just now define some objects where we collect certain kinds of partial derivatives. So the first object that we define is the gradient vector. And we will denote the gradient vector of some function, in this case psi, with this Nabla operator. And the gradient of psi is a column vector, so I wrote it as a row vector transpose to have some more space on this slide, but it's a column vector. And each entry represents one possible partial derivative that we can find. First order partial derivative of psi. So the first entry is the partial derivative of psi with respect to the first entry of the input vector. The second entry is the partial derivative of psi with respect to the second entry of the input vector, and so on until we reach the dth and final entry of our input vector. And from this definition follows that the gradient vector is of dimensionality d, because it has d entries. And the Hesse matrix is the collection of second-order partial derivatives of that function psi. And we collect these second-order partial derivatives as follows. So for the first row of the Hesse matrix, we have all those second-order partial derivatives where we first take the first-order partial derivative with respect to the first entry of our input vector. So we have the second-order partial derivative of psi with respect to x1, and then any of the other entries, right? So here's x1 twice, here's x1, x2, and so on until we have x1 and then finally xd. And for the second row, we have exactly the same, but this time the first variable that we differentiate with respect to is the second entry of our input vector and so on until we reach the final row of our Hesse matrix, where we start the second order partial derivative with the d's and final entry of our input vector. And following this idea, we see that the Hesse matrix has d rows and d columns. So the dimensionality of the Hesse matrix is d times d. And then finally, there's the Jacobian matrix, which we might be interested in finding when we are dealing with a function phi that has n-dimensional output. And the Jacobian is defined as the collection of first-order partial derivatives of this function with n-dimensional output. And the way that we collect these first-order partial derivatives is that we consider each of these n entries in an output vector as individual multivariate functions, like we did in this case where we considered this function psi. And for each of these entries, we find the gradient vector. We did that with psi. So we can do this with the individual entries of phi again. And then we collect these gradients as follows. So the first row of this explicit formulation is the transposed gradient of the first entry of the output vector. And similarly, the second row is the transposed gradient of the second entry of the output vector, and so on. And we do this n times because the output vector has n entries. And this is our Jacobian matrix. And we can again find the dimensionality of this. This will be n times d. So just like earlier, I want to give you the opportunity to test your knowledge. And again, I will take a minute to fill this out myself and then we compare results. So see you in a minute. Welcome back. So the gradient vector of psi is defined as the collection of first order partial derivatives. And we can take the partial derivatives with respect to alpha and beta. So we have two elements. And we now want to find the partial derivatives of this function with respect to alpha and beta. So let's do it for alpha. We see that this bit turns into 3 alpha to the power of 2. This turns into 0, and this one is minus beta. And we are left with 3 alpha to the power of 2 minus beta as the first entry for a gradient vector. And now let's differentiate this with respect to beta. And we see that this one will be 0. This bit will be 4 beta to the power of 3. And this bit will be minus alpha. And this is precisely what the second entry for our gradient vector will look like. 4 beta to the power of 3 minus alpha. Okay, so this wasn't that hard. Now, let's find the second order partial derivatives, or the Hesse matrix of this function. And we first find this element. So we take the partial derivative of that function with respect to alpha, and this is this entry in our gradient vector. And we differentiate again with respect to alpha. Okay, so this 3 alpha to the power of 2 bit becomes 6 alpha, and this minus beta bit will become 0. And this is what we have in this first entry, 6 alpha. Then we go for this entry, and this is the partial derivative of this entry of our gradient vector with respect to beta now. And we see that this first term will be 0, and then minus beta will become a minus 1. And this is what we have here. And then we go to the second row, where we will consider the second entry of our gradient vector. And we will now differentiate this entry with respect to alpha. So we see that this first bit will be 0, and this bit will be minus 1. And this is what we have here. So let's find this final entry of our Hesse matrix. So we consider this second entry of our gradient vector again. And we differentiate with respect to beta. And this leaves us with 12 beta to the power of 2. And this is the final entry. Now we want to find the Jacobian of this function phi. and phi has 3-dimensional input and 2-dimensional output. So we are left with an object of dimensionality 2 by 3. And we find the Jacobian by finding the gradients with respect to the individual entries of the output vector of this function phi. So the first gradient is the collection of these first-order partial derivatives. So we take the first entry of phi and find the partial derivative of that with respect to alpha, beta, and gamma. And we take the partial derivative of this function with respect to alpha first. And this will be 3 alpha to the power of 2 plus gamma times the cosine of alpha. And this is the first entry. Then we differentiate this function with respect to beta. And we are left with 3 beta to the power of 2. And this is it. And finally, we differentiate this function with respect to gamma. And we see that this will be just sine of alpha. And now for the second entry of the output vector of phi, we differentiate this function with respect to alpha, and we see there's no alpha at all, so the derivative will be 0. Now we differentiate with respect to beta, and we see that this will be gamma times the cosine of beta. And finally, we differentiate this function with respect to gamma, and we are left with 2 gamma plus sine of beta. 2 gamma plus sine of beta. Now, if you were able to solve these two sets of exercises, you should be ready for the material. And even if your knowledge was a little shaky, I guess you'll be fine. So let's have a look at the rest of the prerequisites. So in this module, there will also be practical assignments. And for those who need a little bit of programming knowledge. So what I expected to know is what variables are and how to define them, what functions are and how to define them. You should be able to use basic control structures, as well as be able to implement basic classes, and some knowledge about algorithms surely doesn't hurt. And we will implement many of our algorithms using NumPy, and just so that you don't have to install a lot of packages, we'll most likely use Google Colab notebooks. But if you have a Jupyter setup on your machine, then you can use that too. And you don't need to know scikit-learn and PyTorch already. So these will be the packages we'll be using most of the time when we do machine learning. And again, there will be no need for you to know them already. We will introduce them in the exercises. Over the course of this module, but also for the rest of the fundamentals of machine learning program, there will be advanced material as well, material that will be hard to digest. And what really helps to get the most out of this material is to know the basics of probability theory. So let us review some of the basic notions of probability theory so that we are all on the same page. So we do probability theory on what's called probability spaces. And these are triplets containing a set of outcomes omega. Sometimes this set of outcomes is also called the universe. We equip this set of outcomes with a so-called sigma algebra. So just intuitively, a sigma algebra is a collection of subsets of omega, where you have a special structure that allows you to calculate the probability of events co-occurring. But let's not go too deep into it. If you don't know about sigma algebras, it's okay. It's just to be formally correct. And then the final object in this triplet is the probability measure P. And with this, we calculate the probability of events occurring. And then we have what's called random variables. And a random variable is a function that maps from this measure space, omega, equipped with its sigma algebra, to some subset of the real numbers, or the r to the d, equipped with the Borel sigma algebra, so that this space is also measurable. So the basic idea is that you need the output space to be measurable, so that you can find all the outcomes in omega that generate a certain range of values that you're interested in measuring. and assign a probability to these outcomes. And this will be the probability of x taking a value in r to the d. So let's write it down. The probability of x taking a value in s, where s is a subset of the r to the d, is equal to the probability of events in omega, for which x omega is in S. Now let's call the set of outcomes that generate the realizations of X that we're interested in A. Let's call this set A. Then the probability of X taking a range of values is equal to the sum of the probabilities of all omega, for which omega is within this set A. So if you haven't seen measure theoretical probability theory before, then it's okay. But this is the basic idea behind random variables. And then we say a random variable is distributed according to a probability distribution. And some common probability distribution that we'll encounter time and time again are the Bernoulli distribution, which is parameterized by this probability of success pi. There's the normal distribution, or the Gaussian density, which is parameterized by a mean value mu, as well as a variance sigma squared. And then there's the Laplace distribution that is also parameterized by two values, namely the mean value mu and the scale parameter b. And then there are, of course, many other distributions that one might consider. So sometimes we may know the family of distributions that we're considering. So for example, if I have a collection of realizations of random variables that have binary expressions, so I have lots of zeros and ones, then it makes sense for me to model the data generating process that gave me the data as a Bernoulli distribution with some probability of 1. And this probability of 1 I will denote with pi. But what is pi? So I can make a guess, but an educated approach to finding the most likely parameter that generated my data is the what's called maximum likelihood estimation. So this parameter theta is estimated. This is the hat is estimation using the maximum likelihood estimation, ML. And this is equal to the parameter in the set of parameters that I'm considering, for which the log probabilities of my data points is maximized. So you may ask yourself, okay, why do we maximize the log probabilities of our data occurring under the parameterized model? And why don't we just maximize the ordinary probabilities? So this is because the logarithm is a monotonically increasing transformation. So the maximum doesn't change in our optimization problem. But what we get is that we turn products into sums. So let me write it down. This argmax problem of maximizing products turns into maximizing the sum of log probabilities. And this behaves much more nicely numerically. And also analytically, it's easier to find the derivative of this expression as opposed to the ordinary product of probabilities. And then there are different kinds of manipulations of densities. So we might have a joint density P of x and y. And if we integrate over the domain of values that y could take, we end up with the marginal distribution, which is just the distribution of x without any y. We can also define what's called the conditional probability. And this is the joint of the two random variables divided by the density of the variable that you want to condition on. Rearranging these expressions yields the Bayes theorem. This is the Bayes theorem. And the importance of the Bayes theorem cannot be understated. So we will make extensive use of the Bayes theorem. And we can also define the independence between two random variables. So two random variables x and y are said to be independent, denoted with this expression, if their joint density decomposes in the product of their individual densities. So this is such a useful decomposition that we often just assume random variables to be independent to make our calculations easier or possible at all, in particular in the context of doing maximum likelihood estimation. And then you should know about the expectation and variance of a random variable x, as well as the covariance of two random variables x and y. And then sometimes we'll make use of the entropy of a distribution, and this is a measure of surprise inherent in this distribution. So this is defined as the probability of x taking some value times the log probability of x taking that value, summed over all possible values that x could take and taking the minus of that, the negative of that. Since the entropy is defined for a density, we can find the entropy of a joint density as well as the entropy for a conditional density. And finally, there's the KL divergence, and this is a measure of how similar two probability distributions P and Q are. KL divergence of PQ is defined as the integral over values a random variable x could take of px times the log of px over qx. And generally, this is not equal to the KL divergence of QP. So the KL divergence is not symmetric. So there are other prerequisites for the advanced material, but it would be just too long of a list to write it out explicitly. So let me just give you a highlight of the concepts that you'll also encounter when studying the advanced material. So we'll make use of a lot of eigen stuff, eigenvalues, eigenvectors, eigenfunctions, eigenspaces. We'll make use of common matrix decompositions, for example, the eigen decomposition and the singular value decomposition. In order to speed up my proofs and calculations, I'll make frequent use of matrix and vector derivatives. And finally, if you know about vector spaces, Banach spaces, Hilbert spaces, this will definitely help in the later sections of this module. But so much about the prerequisites. We're ready to now start with the formal setup.